So hello and welcome to the third video, the short one on just some questions relating to driven damped oscillators. So we'll go ahead and we'll have a look at the question on the slideshow. So damping and resonance slide, we're going straight to the question, limited space. So this question is about a driven mass spring system. We're given a bunch of values for it, but it says that the system has a limited space that it can move in. The mass can only move up to a maximum range of motion of 1.2 meters. And so with all of that information that we've been given, we want to figure out the maximum drive force that we can set on our driving system so the object will not collide with the edge of its environment. So feel free to pause the video and have a go at this if you haven't yet. Try and figure out what you can. It is a little bit of an odd approach to a question that you may not have encountered something along those lines. But hopefully you can get started on it, at least think about what we're looking at. What we'll do, once you've all had a go at that, continue on with the video and see how you got along. So I'm going to jump over now to my document camera instead, and we'll have a go at figuring out the answer. As I always suggest, first thing, well, technically the first thing is to think about the system and try and understand it. But this is a fairly simple system in the sense that we've got a driven oscillator and we're just trying to find one of the properties that limits another one. So what we've been given is that we've got some mass spring system. All right, we've got some mass spring system and it's being driven, so we know that we're basically going to get some range of motion, right? So it might go minimum position here, maximum position here, and we're told that the maximum, the distance from this maximum to this minimum is 1.2 meters. So I guess the trick with this question is realizing that that range of motion being 1.2 meters is from minus A to A, and we've still got to have our zero in the middle. So A is actually going to be half of that range of motion. So that's probably the biggest trick that we've got on this question. So A is equal to 1.2 over 2 equals 0.6 meters. So that's our amplitude. That's the maximum amplitude we can get. So I'll put that in, I'll put max. A max is 0.6 meters. So that's the biggest we can allow the driven system to get. So now I'll go ahead and write out all the other information we've been given. We've got a mass of 620 grams, which of course we want everything in SI units, so 0.62 grams. We've got a spring constant of 95 newtons per meter. We've got a driving force period of 0.55 seconds. So T external is 0.55 seconds. And we've got a damping constant B of 0.11 kilograms per second. I think that's all the information we've been given. We've already talked about the amplitude, so we've got that as well now. So then what you'd need to do is find the appropriate formula. I will write it out here. You would probably just look at the page and go straight to doing some calculations, or potentially. So the formula that we're looking for is one that has our resulting amplitude of the driving motion. Remember, we haven't been asked anything about the frequency that the system will move at or anything to do with the equation of motion. All it's asked is what value will give us this amplitude as a maximum. Right? So A naught is equal to this big fraction, F naught on the top, mass times the square root of omega external squared minus omega naught squared. That's all squared. Then we've got our fraction here, omega external squared over m squared, and that's all within the square root. So that's our big ass fraction. Right? We've got to now rearrange it because we want to find F naught. That's what we're looking for. We're looking for F0. So that's quite simple. We just multiply both sides by this whole bottom of the fraction. So F0 is equal to A0 times M times, I'm just going to do that, that whole square root. So that's what we're looking for. And we're actually looking for the F0 so that this is less than this when it's equal to 0.6. So we want to find the maximum driving force that fits within this. So now you've almost done the whole problem. What we have left to do, though, is figure out all the terms that go into this. The mass, we got told. The drag coefficient, we got told. That's the mass again. But we've still got the driving frequency and the natural frequency. So we also have to figure those out. Let's just think about what they are. The natural frequency is equal to the square root of k over m. Right, so that's nice and straightforward for this one. And I've got my handy cheat sheet that I prepared earlier that tells me that that is, am I even looking at the correct one? Yep, so 62, 95, 55. So my natural frequency is 12.38 radians per second. So there's my natural frequency. Then we have to figure out the driven the external frequency. So the external frequency, we've been given the external period. We need to turn that into a frequency. So it's 2 pi over t external. And so hopefully if you're following along, you get out 11.42 or 42 radians per second. And so now you've actually got what you need to do this calculation. All right, so we've got the mass here, mass here. That color isn't showing up very well. We've got the mass and the mass, that goes there and there. We've got F0 is the one we're looking for. We've got our amplitude here and up here. All right, back up there, 0.6. And we've just figured out, we've also got B. We've got our B term in here, which is given to us here. And then we've just figured out our different driving frequencies. Right? Sorry, two different frequencies. One's the driving frequency, and one is the natural frequency. And so now you can go through and fill out that equation, put in all those values, and get a result. I'm not going to show you myself doing that because that's just a calculation, but hopefully you get out that the resulting force, in order for it to be equal to 1.2, right, so when A0 is equal to 6, F0 should be equal to 8.48 newtons. But of course, this is saying that that's the maximum amplitude, so anything less than that will be fine, because the question was, what's the maximum driving force we can have? So anything less than that 8.5 newtons, 8.48 or 8.5 newtons, will not reach the maximum range of 1.2 meters. So that is the answer to that. We'll jump over to the next question. So there's the answers there. Jump over to the next question. This is about driven dynamic oscillators being turned into damped harmonic oscillators. So driven damped oscillators turned into driven harmonic. I'm getting my words all mixed up. Driven damped oscillators getting turned into damped harmonic oscillators. All right, I can almost get that out, bit of a tongue twister. So the question here is, given this graph, we've got three different systems, three different driven damped oscillator systems. So you can see that they're not the same identical system because they're different when we're at higher and lower values of a driving frequency. Remember the graph we saw where we had 3 of the same system with just different damping coefficients? They looked exactly the same apart from that peak, whereas this one, everything about the graph is the same. So the systems are completely different. And the question is simply, if once all this investigation has been done and we've figured out this graph, so we know these are the resonance curves, if we then disconnect the driving force, the driven part of the system, so it's now just a damped harmonic oscillator, and we set each of them oscillating, we give them each the same amount of energy, start them oscillating, the question is which will oscillate for the longest time? Which of those 3 oscillators? You've got the gold, the brown, and the green. Right, so gold is this one here, brown is the middle one, and green is the top out here that goes lowest there. So those are the 3 systems, and which of them is going to oscillate for the longest time? I'm just going to talk for a couple of seconds here to give you a chance to pause the video, have a think about it, do try and answer the question yourself. Don't just rely on listening to me and going, oh yeah, that makes sense, because that won't help you understand if you know how to solve the question without my help. Right? So have a go at it. Once you're ready, resume the video and see if you get the same conclusion as I do. Right, so here's the solution. You need to think about the Q factor. Right, remember or Q value. Remember the Q value, when it's a narrower, higher peak, you've got a higher Q value. Right, so that means just by looking at this graph, we can tell that the gold oscillator has a higher Q value, the brown one is in the middle, and the green one has the lowest Q value. It's got the widest, shortest peak. So those are the different Q values. Now we have to remember what the Q value means, not just for driving, which tells us about this peak, but for damping. So the Q value for damping said that the larger the Q value, the less damped the system was. And remember that the less damped it is, the less energy it loses every cycle. So if it's losing less energy because it's got a higher Q value, that means it will oscillate for longer before it's lost all its energy and goes back to just sitting in its equilibrium position doing nothing. So the higher the Q value, the less energy lost to damping, therefore the longer it will oscillate for. Right, so as you can see, that's the answer on the next slide, but hopefully that made sense before we got to this slide, before you read it. And that's all we've got, just those 2 questions, one dealing with the equations and one dealing with the theory, the concept of the Q value. So hopefully that all makes a bit of sense, and I will see you all at the next video.